Hey everyone, I'm Jennifer, and this video is going to be on the hydrohalogenation of alkenes and alkynes. So, as a refresher, hydrohalogenation is an electrophilic addition reaction, and it involves an alkene or alkyne reacting with a hydrogen halide such as HCl, HBr, or HI. Those are all common hydrogen halides. Okay, so it is important to remember for hydrohalogenation that this follows Markovnikov's rule. So I'm just going to write Markov. And what this tells us is that the hydrogen atom will attach to the carbon that is less substituted. And the X, which is the halogen, so in the example above, that's the chlorine, will go to the more substituted carbon, as that is the better steric position. And when we think about it, this makes sense because when the hydrogen from the hydrogen halide is added to the less substituted carbon, then a more stable carbocation can be formed. Okay, so now we can talk about the mechanism up above. So in this reaction, this double bond is actually acting as a nucleophile. So because it is a nucleophile, it will attack this hydrogen, and then this causes the bond between the hydrogen and the Cl to also break. And as we talked about earlier, the hydrogen will want to go to the less substituted carbon. And in this particular case, the hydrogen does not have a preference as both carbons are secondary. So the next step, similar to SN1 reactions, is that a carbocation will form. So the hydrogen I just chose, it will go to one direction, but again, it doesn't really matter in this case. And that leaves the stable carbocation in this position, and then we also have a Cl minus in the back. And again, similar to SN1 reactions, after we form the stable carbocation, we need to ask ourselves if migration needs to happen for there to form a more stable carbocation. But because this is a symmetrical structure, then no migration needs to occur. But I'm going to write it just so we don't forget. Okay, so I moved on to the next page because we were running out of room. But now that we know that we don't need to move this carbocation, this chlorine, let me go back, from the HCl, now this can act as a nucleophile and attack the carbocation, as that is the electrophile. So again, we went from nucleophile to electrophile from the double bond. And in this next step, we're also going from nucleophile to electrophile. So let me just draw that. And then this will form a new bond attached right here. And then we still have this hydrogen. Okay, so as you can see, hydrohalogenation has a fairly straightforward mechanism, and it's following patterns that we've seen again and again of nucleophile wanting to attack an electrophile, and also looking at carbocation and what will be the most stable spot for that. In this case, it was a symmetrical molecule, so that made it simpler for us. Okay, so we can go over another example, and already we see that we have an alkene and an HBr, so this is a sign that it will be a hydrohalogenation, as this is one of the more common hydrogen halides. And I just added a substituent that I had forgot to add, so it's not a symmetrical compound again. But similar to before, the mechanism will start with the double bond going to the hydrogen, because again, the double bond is a nucleophile in this first step. And again, remembering that hydrohalogenation follows Markovnikov's rule, so this hydrogen will want to go to the less substituted carbon. So first we see that this is tertiary carbon, and this is a secondary. And I'm realizing that it's a little confusing because here it looks like there's 4 bonds to the carbon, but we have to remember that this double bond is breaking as it attacks the hydrogen. So this is tertiary and this is secondary. Okay, so now would be a good time to take a moment and see if you can figure out to which carbon the hydrogen will go to. And before we even do that, I forgot to draw in the bond breaking between the hydrogen and the bromine. Okay, so now we can draw the intermediate, and hopefully you were able to figure out that the hydrogen will go to the less substituted carbon, which is the secondary carbon right here. So this will have the hydrogen, and that means that the carbocation will be left here in a tertiary position, so it is more stable there. And remember that we have this bromine, this negatively charged bromine, still here. And, before the nucleophile attacks, we have to ask ourselves the same question. If the carbocation wants to migrate, but it's already in a tertiary location, so it wouldn't really make sense to move it. So now the bromine can attack. So I'm just going to draw that arrow. And again, this will result in a new bond with the bromine. And again, we can see that this final product is Markovnikov, as the hydrogen is on the less substituted carbon and the halide is on the more substituted carbon. Okay, so the next reaction we're going to look at is still hydrohalogenation, but this time with alkynes, and it's very similar to alkene hydrohalogenation. One difference is that alkyne hydrohalogenation can react multiple times depending on how many equivalents are used. And as a reminder, alkyne hydrohalogenation also follows Markovnikov's rule, just as with the alkene reaction, so that's important to keep in mind as we follow the steps of the mechanisms. Okay, so similar to the alkene reaction, the triple bond will attack the hydrogen, and then this will cause the bond between the hydrogen and the halide to break off as well. So again, similar to the alkene reaction, the intermediate will have a stable carbocation, and that will be in this carbon. And we still have our negatively charged halide, and that is going to want to attack the carbocation, just like the alkene reaction. So then this is going to form a new bond with an X can represent any hydrogen halide, like chlorine or bromine. And I like to show the hydrogen but right here, but you don't have to include it. So a lot of people will also just draw this structure like this. Okay, so I moved to a new page because we ran out of space. But let me go back here to show that this was one equivalent So technically we would be done here and the reaction would stop here. But we can show what this would look like if there were two equivalents, because now this is an alkene, so the reaction can keep going. Okay, so hopefully this will go quicker since we've already done this. But again, this is assuming that we had excess or two equivalents. So then here we have this alkene, and this will take the hydrogen, bond between hydrogen and the halide breaks, and then we form our intermediate, and that will look like this, where the H is here, the X is here, and this is the most stable carbocation. And just like before, we still have the negatively charged halide, so that will be attracted to the carbocation, forming our final product, which will be two X's here instead of the one. And again, this is assuming we have two equivalents. Okay, so as you can see, alkyne reaction or hydrohalogenation reactions are very similar to alkene reactions. They just have the possibility of reacting more. So it's not necessarily more difficult, it just, there can be more steps. Okay, so I think we have time for one more example. And since we've been going through these mechanisms several times, for this problem, we're going to see if we can predict the product without necessarily having to draw all of the mechanisms. And I'm going to make this excess, which could give us a hint into how this is going to result in, or what the final product will be, since we know it will react multiple times. Okay, so actually we can start there. If we look at this and see that it's going to react multiple times, that tells us that the final product should not have any double or triple bonds left. Additionally, because it's reacting with the HCl twice, we know that there's going to be two of these halides left instead of one or zero. Okay, so we can draw the skeletal structure without any double or triple bonds. And now the last thing is figuring out where the two chlorine atoms will be. And because we know that this is following Markovnikov's rule, that tells us that the carbocation is going to be in the most stable location, and this is primary, so it can't go there. And typically in the hydrohalogenation of cyclic alkynes, there is no migration of the carbocation, which means that we can predict that the carbocation will be here and the two chlorine atoms will attach here. So this is our final product. And we actually do have a little more time left, so we can show how this happens. And again, hopefully this should be quicker now that we've done it so many times. So this will be the carbocation intermediate. We still have the hydrogen here, and then a plus sign there, because that's where the triple bond used to be. And remember, we have this negatively charged chlorine atom. Oh, the lone pairs are not really working right now, but that's okay. We can pretend they're all there. This attacks the carbocation, and this leads to a new bond. Oh, suddenly I can't draw anymore.